Yeah, can somebody confirm if my open boot screen is visible? So, uh, hello everyone. Um, Good evening. And so, in today's session, we will be discussing the aerodynamic problems from GATE 2018 paper. And let's go ahead and get started with these problems. So, in the first question, what they're asking is, there's a NACA 0012 airfoil that has a trailing edge flap. So imagine you have a airfoil, something like this. That's a symmetric airfoil. And it has a flap which is at the trailing edge. And we know that flaps are kind of for developing high lift, especially during takeoff or landing conditions. And the airfoil is operating at an angle of attack of 5 degrees with the undeflected flap. So let's say if my angle of attack is 5 degrees, right? And my flap is undeflected, so we are not using the flap yet. Um, and what they're asking is if the flap is now deflected by 5 degrees downwards, the CL versus alpha curve will. So what they're asking is if you deflect the flap, how will your CL versus alpha curve, which typically is, let's say for a symmetric airfoil, will look something like this, right? It starts from 0 and then goes up to the stall angle. And imagine we are looking at an angle of attack of 5 degrees. All right. Now what they're asking is what will happen um, if you deflect the flap. So to analyze that, I've just kept a figure over here, which basically compares an airfoil. In this case, it's a non-symmetrical airfoil, but just to explain the concept, the scenarios of CL versus alpha with flap and without flap. So what basically the addition of flap does is for a given angle of attack, it basically shifts the curve a little bit upwards. So the blue curve and the red curve, if you compare, what it is exactly doing is it's shifting for a given, let's say, at a given angle of attack, let's say 5 degrees. Here you can see, it corresponds to some value. And, with flap, it's basically a much higher value. So it's in fact shifting your curve, your CL versus alpha curve a little bit higher. And in addition to that, there is also a small shift that happened towards the left, which is not very pronounced. But that still happens. As you can see, there's a small shift. There's a reduction in the stall angle of attack, as you can see over here. So here, with no flap deflection, the stall angle of attack is around 15 degrees, while with flap deflection, it's slightly reduced. So once you deflect the flaps, your CL versus alpha curve, it maintains the slope. As you can see, whatever was the slope initially, the slope is maintained. And there is a shift towards up and a slight shift towards the left-hand side. Um, and and um, and this reduction in the stall angle of attack, as you can imagine, because now you are for a given angle of attack, what is essentially what's happening is that you're increasing your CL over your airfoil, and hence you're reaching your stall angle of attack a little bit faster than usually you would be reaching. Um, so Out of the given option, the right option is, so what they're asking is whether shift shows the right and slope increases, shifts left, slope increases, shifts left, slope remains the same, shifts right, and slope remains the same. So the right option here is option C, where there is a slight shift towards the left, but more importantly, there's a slight shift. There is a huge shift upwards, but which it's not there in the options, and the slope stays the same. There's no change in the slope at all while using a flap. So the right option is option C. All right. Any questions? Moving ahead. So in this question, what they're asking is the velocity profile in an incompressible laminar boundary layer is as shown in the figure below. So they're showing a velocity profile by capital U, which is your velocity profile divided by the free stream velocity along height along the vertical distance. Why? U is the free stream velocity, Uy is the streamwise velocity component. The area of the black shaded region in the fill bigger below represents the boundary layer thickness, momentum thickness, displacement thickness, and shape factor. So, and not if you look at the options over here, what you can see is, um, you know, let's say they're talking about what this shaded region, what quantity does it actually amount to, or what quantity does it actually represent? So this quantity, what they've shaded over here. So typically, if there was no boundary layer, right, your velocity profile would look something like this, right? Velocity profile would look like uniform in nature. There's no deficiency or anything like that. And because of the presence of the boundary layer, now it has become something like this, right? As shown in the red color, because it has a reduced area, as you can imagine. All right. So now the shaded region is this region. That is basically whatever is left out. So whatever is left out, uh, so your initial profile minus your free stream profile minus your velocity profile in the boundary layer. So this area basically represents nothing but how much of deficit of mass is happening because of the presence of a boundary layer. So at a given section, so much of deficit of mass or velocity, let's say, or mass flow rate, to be precise. So that so much mass flow rate deficit is happening at every section because there is a boundary layer that is forming. And we know, as a matter of fact, that the deficit of mass is basically used to calculate nothing but your displacement thickness. So if you remember, the displacement thickness is primarily calculated by taking how much is the mass flow rate deficit in every section, and then trying to figure out how much should be the let's say additional thickness in that particular location, by how much your boundary should be shifted to accommodate for that deficit of mass, basically. So this deficit of mass flow rate, to be precise, basically tells us, what is your displacement thickness. And if you look at the other option, boundary layer thickness, it's a very general term. The boundary layer thickness is basically the height from the bottom towards the end of the boundary layer. So this shaded region, it does not really exactly represent that. Your momentum thickness does not only takes into consideration this shaded region, it also takes into consideration the momentum that is being carried. The shaded region does not really represent the momentum; it just only represents how much of a flow rate deficit is present. The mass flow rate deficit, not the momentum flow rate. And displacement thickness, as we mentioned, it's basically what the shaded region represents. And shape factor is nothing but the ratio of displacement thickness to the momentum thickness. So that's an entirely different ratio that typically we calculate for certain shapes. Just to compare. how much of refinement in the boundary layer we get when you go from just because momentum thickness is usually lower than displacement thickness. So by adding more complexity to the boundary layer definition, we are trying to refine how small the boundary layer should be, and basically trying to define it. So that is an entirely different concept altogether. So this definitely won't represent it. So the right option here is option C, displacement thickness. All right. Any questions here, guys? Go to the next problem. The pitching moment of a positively cambered NACA airfoil about its leading edge at zero lift angle of attack. So what they're telling you is you have a positively cambered NACA airfoil. There's a NACA airfoil which is positively cambered. Imagine. All right. And it is at zero lift angle of attack. So it is actually operating it at alpha L equals zero. All right. Basically, it's not producing any kind of lift. All right. So that is the scenario in which it is operating. And what they're asking is the pitching moment at the leading edge. What would be the value of pitching moment at the leading edge? Whether it would be negative, positive, cannot be determined, or it would be zero. What do you guys think is the option here? At zero lift angle of attack, what would be your moment at the leading edge? Any idea? Negative. Not right. Okay. So the right option here is negative, and the reason being, so if you look at the expression from thin airfoil theory for the moment at the leading edge for a cambered airfoil, so Cm at the leading edge, all right, is given by negative of Cl by 4 plus pi by 4 into A1 minus A2. So we know that um, it's operating at alpha L equals 0. So the Cl value is 0 for it, right? The Cl is 0. So that basically cancels this guy out. And what we have left is negative of pi by 4 into A1 minus A2. All right. And typically for a NACA airfoil, now I'm not talking about any general cambered airfoil, but typically for NACA airfoils, your A1 will be greater than A2. And hence your moment at the leading edge would be, negative. That is one way of looking at it. And also other way of looking at it is, let's say you take the moment at the quarter chord, right? Or the aerodynamic center for that matter. So we know that cambered airfoil will have some moment at the inherent moment at the aerodynamic center, and it's usually a negative moment, right? It's a pitching down kind of moment, typically for a cambered airfoil, a positively cambered airfoil. All right. Now you are in a scenario. Imagine this is your aerodynamic center. So let me just this, let's say, call it XAC, the distance from the aerodynamic center to the leading edge. XAC, let me call it. So you have a lift over here. So let's say if I were to find the moment at the leading edge from based upon your lift and moment at the aerodynamic center, I would calculate it as moment at the aerodynamic center, and then transferring it to the leading edge, I'll have minus lift into XAC. All right. And in our case, lift is basically zero because it's a zero lift angle of attack. So this guy goes So moment at the leading edge is exactly equal to moment at the aerodynamic center. And we know that a positively cambered airfoil, especially NACA airfoils, have negative moment at the leading edge, a negative moment at the aerodynamic center. So hence the right option here is option A, right? So there are in these two ways you can try to imagine this problem. Clear, guys? Any questions? So let's look at the next problem. In a low-speed wind tunnel, the angular locations from the front stagnation point on a circular cylinder where the static pressure equals free stream static pressure. So even in yesterday's session, we did a problem which is very similar. So what they're asking is, you have a cylinder in a low-speed wind tunnel, and what they're asking is, so this is your front stagnation point. From the front stagnation point, you need to find the points on the cylinder, on the surface of the cylinder. You need from, let's say, if you go from the front stagnation point, where do you find? You need to find those angular location for free stream static pressure equals, well, the static pressure is equal to free stream static pressure, or in other words, where P equals P static, P infinity. Sorry, P static is P equals P infinity for that matter. So positively camber at zero lift CL, it can produce lift. No, it can't produce lift. Zero lift, angle of attack. If it is at zero angle of attack, it can produce lift. But if it is zero lift angle of attack, then it can't produce lift. Right? So your P equals P infinity. So what happens to CP? P equals P infinity. So CP is defined as P minus P infinity by your dynamic pressure, right? Like half rho infinity and V infinity square, right? So when P equals P infinity, your CP will basically be zero. So we are going to look at locations where my CP is zero. And we know from potential flow theory that Cp over a non-lifting cylinder can be expressed as 1 minus rho sine square theta, right? And this, is what we are equating to zero and figuring out what are those theta locations. So this basically tells us that my sine theta is nothing but plus minus half, right? So your sine theta is plus minus half at four locations. One is when theta equals 30 degrees. I'm basically calculating this angle from, let's say I'm going in this way. So from theta equal to 30 degrees, your sine theta is basically plus half. And at theta equals 150 degrees, again, your sine theta is basically positive half, right? 50 degrees. And then at theta equals 210 degrees, your sine theta is negative half. And at 330 degrees, your sine theta is again negative half. All right. So 30, 1 is positive half, and at 210, 330, it is negative half. Now, in the following, in the options given below, they are asking us what is the location from the front stagnation point, right? Let that. So they're asking you the locations from the front stagnation point for that matter. So you need to measure it with respect to the front stagnation point in both the directions. All right. So from the front stagnation point, if you go plus 30 degrees, so always anti-clockwise direction is taken to be positive in a mathematical sense, and clockwise direction is taken negative in mathematical sense, not in aerodynamic sense, but mathematical sense. So if I go plus 30 degrees, that is, to this location of 210 degrees, I get, a location where sine theta is minus half. And if I go minus 30 degrees to a location where theta is 150, I get a location where my sine theta is positive half. All right. So, so from the front stagnation point, you need to go plus minus 30, and you will reach locations where my sine theta is plus half or minus half, either one of them, and correspondingly making your CP to be 0. And that basically means my P equals P infinity, right? So that basically tells us the right option here is B plus minus 30. The other option, 38, definitely not. At 38 degrees, from anywhere you calculate, you're definitely not going to get sine theta equal plus minus half. And theta equals plus minus 60. If I go plus minus 60, you'll definitely not get theta equals half. You'll get probably other values of sine theta, not half. And if you don't get half, you will basically not be able to make P equals 0, and correspondingly P minus P infinity to be 0. All right. So the right option here is plus minus 30. Okay, guys, any questions? Let's look at this problem. The magnitude of x component of a unit vector at the point 1, 1 that is normal to equipotential lines of potential function by r equals 1 by r square plus 4, where r is root of x square plus y square is an interesting problem. So what they're telling us that you have some equipotential lines given by phi equals 1 by r square plus 4. All right. And you want to figure out like there is a point in my xy plane called 1 by 1 comma 1. All right. 1 comma 1. All right. If I go one distance along my x and then one distance along y, that's the point. Now you want to find a vector, a unit vector, which is passing, which at this particular point, and it is normal to this equipotential line. All right. So let's try to figure out how these equipotential lines look like. All right. So let's me, the way to figure out what is the shape of an equipotential line is basically to equate them to some constant. Let's say C1. And then if I do, the cross, if I take C1 to one side, R square plus 4 to the other side, so I get R square plus 4 equals 1 by C1. All right. So your R square is equal to, 1 by C1 minus 4. And your R is nothing but root of plus minus 1 by C1 minus 4. All right. And we take, values of C1 such that this square root is real, not imaginary. Only then we'll be able to sketch it, right? So this is nothing but equation of a circle, right, of some radius. All right. So so it will be your equipotential lines will look something like this: circle of one radius, circle of another radius, and circle of maybe a different radius. So they'll be like concentric circles with the center at your origin. All right. Now let's say if you were to go ahead and then figure out what is the equipotential line, equation of the equipotential line passing through this point 1 comma 1. So if I try to take what is the, let's say if I try to draw a circle, so we know that equipotential lines of this equation of this form are concentric circles in nature. So we know that I need to figure out what is the equation of the equipotential line passing through this point 1, 1. So what would be the value of r for this point 1, comma 1? So that will be nothing but r equals, in the question they've told you r equals square root of x square plus y square. Here x is 1 and y is 1. So here I do 1 square plus 1 square. So I get r equals square root of 2 for that matter. And now if I substitute r equals square root 2 in this equation, what I'm going to get is, so phi equals 1 by r square, which is 2 plus 4. So that will be phi equals 1 by 6. So if I take this, let's say I write r1 plus r square by 4 equals 1 by 6. All right. And if I rearrange the terms, it would look something like this. So r square plus 4 equals 6. And your r square equals 2. So it's basically nothing but a circle of radius root 2, right? So r equals plus minus root 2. All right. So this is going to be the equipotential line of this particular form passing through this point 1, comma 1. All right. So that's something which we have figured out. Now you need to figure out a unit vector which is perpendicular to the equipotential line passing through this point 1, comma 1. So we know that a line from the center to any point on a circle is going to be perpendicular, like a normal a radial vector from the center to any point on the circle is going to be perpendicular to the circle at any given point where it intersects, right? So if I were to draw the radial vector from my center to this point 1, comma 1, it basically is telling me that um, this line will definitely cut through the circle and cut through the circle of radius root 2, and it will be normal to the point wherever it is intersecting, right? Because the radial vector is always going to be normal to whatever point is lying on the surface of the circle, lying on the edges of the circle. All right. So we know, as a matter of fact, now this radial vector is a vector which is, so here the idea is to find out the vector that is normal to the equipotential line. So now we know that the radial vector is normal to the equipotential line at this point 1, comma 1. Now only thing that is left to do is basically find the equation of this radial vector. All right. So this vector which basically intersects at 1, comma 1, and the origin is basically at 0, comma 0. All right. So the way we would characterize the equation is nothing but the vector. Let me call it as v vector would be nothing but 1 minus 0 I cap. So basically, the way you would characterize the vector would be nothing but x2 minus x1 I cap, and y2 minus y1 j cap. Right? So this is how you would characterize your vectors. So if we characterize your vector given 2 points. So here, let's say this is x2 and y2, and this is x1 and y1. So you have vector of the form 1, comma 0, and again 1, comma 0 j cap. All right. So the equation of your vector is basically 1 I cap plus 1 j cap. All right. And now they're basically asking you to find find it as a unit vector for that matter. All right. So if you were to try to convert this to a unit vector, you need to divide it by the magnitude of the vector, right? If I were to convert v to a unit vector, what do? I take the vector then divided by the magnitude of the vector. And magnitude of the vector is nothing but square root of 1 square plus 1 square, right? The square, square, and sum of summation and the root of the individual terms of that vector. This would be nothing but root 2. So each term would be 1 by root 2 I cap plus 1 divided by root 2 j cap. All right, so this basically represents a unit vector. Basically, this vector, which is a unit vector now once you divide by the magnitude, which is normal to this point, which is normal to the equipotential line at the point 1, 1. All right. And in the question, they're asking you what is the x component of this unit vector. X component of the unit vector is nothing but 1 divided by root 2, and that will take up some value around 0.707. So this is basically how you would solve this problem. Clear, guys? Any questions here? Questions, concerns? Move ahead. A pitot probe on an aircraft in a steady level condition records a pressure of 55,000 Newton per meter square. The static pressure and density are 45 to 80 Newton per meter square and density is 0.6 respectively. The wing area and lift coefficient are 16 and 2 respectively. The wing loading of this aircraft is. All right. So there is a pitot probe which is kept on an aircraft, and then that is measuring a pressure of 55,000. So we know that a pitot tube will basically measure your total pressure, right, or your stagnation pressure. So whatever this value 55,000 is basically your stagnation pressure. All right. And when we were solving Bernoulli equation related problems, we have seen that a pitot tube will only have pitot tube will basically bring my flow to rest, and hence you can calculate the stagnation pressure. And when you combine it with the static probe, and then you take the difference, that when you basically get your dynamic pressure, right? So in this case, they only have a pitot tube, which is calculating your stagnation pressure. Now there's a static pressure calculation as well. Static pressure is 45 to 80, and the density is 0.6. So you have your P static as well. And what they want in the question is the wing loading. Wing loading is nothing but your weight of the aircraft divided by the surface area of your wing. And weight of the aircraft is, so in this case, the aircraft is in steady level condition. So weight of the aircraft will be nothing but lift. And lift can be written as your lift coefficient. They have given you what is the lift coefficient value times half rho infinity v infinity square times s divided by s. So s and s you can cancel out. The wing loading can be written as CL into half rho into v infinity square. So they have given you what is the CL value, which is 2. Density is also given to you. What you don't have is your velocity. And velocity you can basically calculate from your P naught and PS. And we know that your P naught minus your P static is nothing but your dynamic pressure, right? Half rho infinity v infinity square. All right. And your P naught is something around 55,000, right? And your P static is 45 to 80, 45, 80, and this is equals half rho infinity v infinity square. All right. So in my wing loading expression, you have a half rho infinity V infinity square. All right. So just replace this with this value. Half rho infinity V infinity square is nothing but 55,000 minus 45,280. So just substitute that over here. So your CL is 2 and your half rho infinity V infinity square is 55,000 minus 45 to 80. All right. So hence your wing loading will turn out to be a value due to the calculation. It will take up a value of around, I think, 18.8 kilonewtons per meter square. So it would be around, sorry, 19.4 would be around 19, and they want the, I'm sorry, not kilonewtons, it would be 19, 440 Newton per meter square would be your wing loading. All right. So that would be basically the value, and they want it in Newton per meter square. So again, you don't have to convert it to kilonewton or anything like that. All right. So this is how you would basically solve this problem. Clear? Any questions, confusions on this? Let's look at this problem. The boundary layer thickness at a location of a sensor on a flat plate in incompressible laminar flow of air is required to be restricted to 1 mm for an effective measurement. So what they're saying is you have a flat plate and you're keeping a sensor on a flat plate somewhere, all right? And the condition for the sensor is that for the sensor to work properly, the boundary layer thickness at that location, wherever it is kept, should be less than 1 mm. All right, so imagine this is your boundary layer growth. And let's say this is the location where my delta is, let's say, around 1 mm. All right. And I can only keep my sensor till this location. Let me call that as X location. If I keep my sensor anywhere beyond this, it won't work for me because the boundary layer thickness is going to get bigger than 1 mm, and my sensor cannot work at any locations where my boundary layer thickness is greater than 1 mm. So what they're telling us, if the flow velocity is 20 meters per second, pressure is 1 bar, temperature is 300 K, and viscosity is 1.789, what is the maximum distance in millimeters of the sensor location from the leading edge? So from the leading edge, what location, let's say X, should I keep my sensor? What distance towards downstream I can keep my sensor such that this condition is satisfied. All right. Or in other words, they're basically asking you what is the distance from the leading edge to the location where your boundary layer thickness becomes 1 mm. Because if I go beyond that thickness, so they're asking me the maximum distance. So that's basically the maximum distance, right? You can't go beyond this value of distance. If you go beyond the value, your boundary layer thickness will go beyond 1 mm, and then your sensor won't work properly. So for this calculation, you can use your standard solutions of, let's say, displacement thickness, which is for a lamina incompressible boundary layer, which is given by the um, boundary layer thickness at any given location from the leading edge on a flat plate is nothing but 5 times the location, 5 times x divided by root of RE. X is a Reynolds number in terms of x. And we know that the boundary layer thickness that we want to restrict it to is 10 power minus 3. We're just converting millimeters to meters. So boundary layer thickness that I'm looking at is 1 mm. It's 10 power minus 3. And I'm in fact searching for the value of x that will basically do that for me. So then if I open the Reynolds number equation, Reynolds number is Rex is nothing but um, rho infinity V infinity into X by mu, right? So in our case, the rho infinity, they have given you the pressure and the temperature, so you can find rho infinity. Your rho infinity would be nothing but uh, pressure divided by R times T, which would be nothing but 1 bar pressure, which is 10 power 5, divided by R is 287, and temperature is 300 Kelvin, right? Just using your ideal gas equation. So that is your rho. So let me just write that down here. 10 power 5 divided by 287 into 300. All right, 287 into 300, and your velocity is 20 meters per second. All right, and you have your x, and then you need to put in your viscosity value as well. That is 1.789 into 10 power minus 5. 0.789 into 10 power minus 5. So let me just draw the brackets just to. So now you have root x and then a x, so you can convert it to, you can cancel both these, and then you can put a x power half over here. All right. Now in this entire equation, only x is your unknown. So if you were to take it to the other side, so your x power half is nothing but your 10 power minus 3 into whatever is inside the square root, that is 10 power 5 into 20 divided by 287 into 300, right, into 1.789 into 10 power minus 5. All right, and then the whole thing divided by 5 as well. All right, and if you were to make this calculation, you'll find your x is around 0.052 meters, which is also equivalent to 52 millimeters. Right. So 52 millimeters is basically the maximum distance from the leading edge you can go downstream before your boundary layer grows above 1 mm in size or thickness. And that is the farthest location from the leading edge that you can keep the sensor. The right option here is, the right answer here is 52 mm. And they want it in millimeters as well. Yeah, guys. Any questions on this? Okay. So that was it. So we have done all the aerodynamic problems in the 2018, and you can see all are simple problems. In some cases, you would just need to remember some formulas, some concepts, and then what to apply where, which values to plug in. If you're very cognizant about that, things should be very, very straightforward. All right. So then, yeah, that is it for today. Uh, thank you everyone for joining in. Right. Close for today, guys.